Hello, today I want to talk about Lewis dot structures. So Lewis dot structures were created by a guy, really smart scientist by the name of Gilbert Newton Lewis. And Gilbert Lewis, I have a soft spot in my heart for because he was nominated for the Nobel Prize 41 times over 35 years and never got a Nobel Prize. So I have a little bit of a soft spot for Gilbert Lewis. I always root for the underdog. But Gilbert Lewis, he came up with this idea that atoms have these valence electrons, and these valence electrons, 8 seems to be this kind of magic number. We talked about this in the octet rule if you've seen some of my other videos. And we can visualize these electrons in the valence, or the outermost shell on the atom, as kind of dots around the symbols. So these Lewis dot structures then are the molecules that form when we kind of follow this process for how these things covalently bond together or share valence electrons. Now you can use Lewis dot structures to talk about ionic compounds, that would be metals with nonmetals, but it's a little less useful that way because of the way that ionic compounds kind of form and different features about them. The visualization from Lewis dot structures really is highlighting the molecular compounds, the covalently bonded compounds. So you're looking for nonmetals with other nonmetals when you're doing Lewis dot structures. Okay, so let's kind of walk through the process and we'll work a couple examples kind of along the way. So the first thing that you need to do is figure out the total number of valence electrons in the structure. So we've talked a little bit in prior videos about electron configurations. We kind of know that the valence electrons are the outermost. So based on where they are in the periodic table, if we kind of look at my beat up periodic table here, carbon is in column 14 or 4A. So its valence electrons are the 2s2, 2p2, so there's 4 valence electrons there. So carbon has 4. If I look to chlorine, chlorine is in our halogens column, so it's in 17 or 7a, which means it has 7 valence electrons. For chlorine, it's the 3s2, 3p5, gets me to chlorine, so that's 7 total. For fluorine, it's in the second period and it has the same number of valence electrons, so that's 7 valence electrons. Now I have 2 of my chlorines, so I'm going to have 2 times the 7 valence electrons, and same for my fluorine, 2 times the 7 valence electrons, and when I add up all of those, then the total number is going to be the total in my structure. So for this one, I have 14, and 14 is 28 plus 4 gives me 32 electrons that I'm going to be working with. So 32 for this compound, which is all nonmetals. So the next thing I need to do is sketch the skeleton of the structure. And the skeleton is going to be a central atom with everything else attached to it. So I have to figure out which one is going to be at the center. Well, if I draw the Lewis dot structures for these, then there's the 4 valence electrons on my carbon. Here's my chlorine with those 3 lone pairs. And here's my fluorine with 3 lone pairs. So when we're talking about how an atom wants to, and kind of our air quotes here, it wants to make this many bonds, then fluorine and chlorine want to make 1 bond each, whereas carbon wants to make 4. Again, heavy on the air quotes there, because atoms don't want to do anything. They're just energetically driven to do it because it is favorable to do so. So when I sketch the skeleton, I'm going to choose as a central atom the one that can connect to the most things. That seems kind of logical, yeah? And in this case, I have 2 chlorines and I have 2 fluorines. So now I can say, well, I started with 32 electrons. And when I connected these, and remember that I can connect these things with this dash here that represents a shared pair of electrons between the two, a covalent bond, then we have 2, 4, 6, 8 that are used. So I used up 8 electrons, which means that I now have 24 electrons left over to play around with. Now my next step is I've determined the remaining electrons. Did that in step 2. And I'm going to distribute them in pairs. So I'm going to put them as lone pairs around the outer atoms. So we're going to make the distinction then between the central atom, which in this case is carbon, and the outer atoms, which are the things that are connected to the central atom. So if we're looking here at my structure, there's the 8 that I've already used. I have 24 electrons to use. That's 12 pairs. So I'm going to put 2, 4, 6 on that chlorine, 2, 4, 6 on this fluorine, 2, 4, 6 on this fluorine, 2, 4, 6 on this chlorine. Now everyone has a full octet, so if I counted up how many I used, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So I had 24 after that first step. I used up 24. I have 0 electrons left over that I can play around with in this structure. So now I need to kind of analyze it and say, well, is everyone happy? And again, happy in air quotes. Is everyone have a full octet or a full valence? Because that's really the drive. That's what the octet rule says, that everyone wants to have a full valence, which is that outermost shell. So I have 2, 4, 6, 8 on my chlorine, so that one's good. 2, 4, 6, 8 on the fluorine, same is true with these guys. And my carbon has 2, 4, 6, 8 from those shared pairs with the chlorines and fluorines. So everyone is happy. This is a valid Lewis dot structure, and I can go from there. I don't have any electrons left over, and so that's it. Now, if I did have electrons left over, so if I did have some that remain, then I would put them as pairs on a central atom. We'll kind of look at examples of that in later times. And then, as kind of a side note here, if the central atom has fewer than 8 electrons, less than a full octet, then you might want to consider double or triple bonds. So let's take carbon dioxide, for example. Our first step, if we're going through the process, is to figure out how many total electrons I have. Well, carbon has 4. And if I look at where oxygen is on the periodic table, it's in column 16 or 6A. So its valence electrons are the 2s2, 2p4. So those 4 in the p and 2 in the s give me 6 total valence electrons, and I have 2 of them. So total, I have 16 electrons to work with for this structure. Now, if I think about the individual elements at play, I have carbon and I have oxygen. What you'll find as you do more of these is that carbon tends to want to be central to structures because of that shape, and that's going to be important if you go on in chemistry to study things like organic chemistry or biochemistry. It's the reason this is foundational to life. So when I look at carbon, I'd say, well, if I'm going to draw the skeleton, I'm going to put carbon at the center and I'm going to attach 2 oxygens to it. So how many have I used up? I've used up 4, 2 in each bond. So that means that I have 12 electrons left over to put as lone pairs. Now I'm going to put 2, 4, 6, 8, 10, 12. So now I've put on the outer atoms the electrons that I had left over in pairs. So I subtract those 12 electrons, and I have 0 electrons left over to play around with. Now, what's the problem with this structure? It's not a valid Lewis structure. The problem comes with carbon. If I look at my oxygens, they're just fine. 2, 4, 6, 8, 2, 4, 6, 8. But my carbon only has 4 valence electrons. So what I have to do is that kind of note up there about considering sharing multiple pairs. And when I share multiple pairs, then I have what is called a double bond or a triple bond, depending on the number of pairs that I share. So instead, I've shared 2 pairs. Now my carbon has 8, my oxygens each have 8, and this is a valid Lewis structure. Now we can also do this for ions. So we can also do this for something like hydronium, for example. Hydronium is the ion that forms when acids react with water. That's the Arrhenius definition of an acid. So if I look at H3O+, then I have to factor in the fact that this has a charge on it, which means that there's an abnormal amount of electrons in it. And that's what gives me that charge, right? An imbalance between the protons and electrons. So let's figure out how many valence electrons I have. From my hydrogens, I have 1 per hydrogen, and I have 3 of them. I have 1 oxygen, which we said that there are 6. And that +1 charge here means that I have 1 fewer electron than usual, meaning that I have 1 more proton than I normally would, right? So I'm going to get rid of 1 electron here when I add these all together. So total, I have 3 plus my 6, right, minus my 1, gives me 8 electrons total to work with. Now if I look at these two, I have hydrogen and I have my oxygen. The one that's going to want to be at the center is the oxygen. It's the one that wants to make the most bonds. So I'm going to attach to it these 3 hydrogens. Now hydrogens are happy with just 2 in their valence. As part of the octet rule, the idea is that you want to have a full outer shell. The outer shell for hydrogen is the 1s orbital, so hydrogens are happy with 2 electrons. So each of these hydrogens is more than happy. It doesn't need any lone pairs. But in bonding them to my oxygen, I've used up 6, 2, 4, 6 in those shared pairs. That means that I have 2 electrons that are left over. And instead of putting those 2 electrons on my hydrogens, I'm going to go back to that 4th rule there. So if everyone else is happy and we still have electrons that remain, we're going to put them as pairs on the central atom. So my central atom here is oxygen, so I'm going to put the pair there, and now I've used up all of my electrons. No more electrons. And everyone's happy, right? Oxygen has 2, 4, 6, 8. Each of my hydrogens has 2. Then we're good to go. Now notation-wise, if I have an ion, this is my polyatomic here, hydronium, in order to show that there's an imbalance of electrons, I'm going to put the whole structure in brackets. And then I'm going to put the charge that's on the polyatomic ion on the outside. So we have the structure in brackets and then the charge, and that tells me there's 1 fewer electrons than what I would expect there to be on this particular structure. Okay, so we've kind of walked through the process of doing Lewis dot structures. We've walked through a couple examples. If you have any questions, feel free to reach out. Otherwise, I will talk to you again soon.